This is a brief outline of the presentation. First, I'll introduce social network analysis, whatever we will be doing later. Then I refresh that representation about networks. And then I introduce network properties, which are the core of the social network analysis. We'll see network level properties, group level properties, node level properties. Then there will be a short section about visualizing social networks, which is not something I'm very good at. Still, it's quite nice and I like the subject. And if there is time, we can see the maths behind the network. So, this is the title of the presentation, and this is about social networks. So first we have to introduce social networks. The social network is a finite set of actors and the relations defined on them. So, we have a network, we have people, actors, social entities, perhaps, something related to people, anyway. So it can be even nations, families, and connections, relationships. In principle, a social network can have different relationships. Still, most of the times when we're doing math analysis, we're just considering one type of relation. What about analysis? The social network analysis analyzes the structure of the relationships among the social, political, organizational actors. So it's about the structure, not really about the individual node properties, unless they're related to the structure. So you can really analyze very different networks using roughly the same set of techniques. These are some parts of social network analysis. We can do analysis on a given network, okay? And see, for example, network ladder, group ladder, and the ladder properties. We'll see them in a few slides. Or we can do something different. We can try to model things, for example, to devise a process which is able to yield such a network. For example, we have a social network we have a social network in service, and we can see which process can yield that network, okay? This can be done in different ways, so we can just try to model one single network very closely, or we may be more interested in the approach, in the mechanistic approach, so we try to see how people connect and see if our model of interaction, people interaction, gives the right network. Or something like the curated approach, where network formation is seen in the process of equilibrium. Okay? And then we can also study processes on complex networks, like, for example, routing a message among people, okay? Or epidemic spread, diseases, that kind of stuff. It's a huge branch, and it has been developed by people from completely different areas. So we have mathematicians, theoretical physics, computer scientists, and people from sociology, of course, but also biologists. They don't do social networks, they do complex networks, but many techniques that have been developed to study technological, biological networks, whatever, can be used for social networks as well. So, different people, different rules. For example, these guys sometimes have algorithms which they do not prove, they terminate, they converge, they work, and they have to work with these guys, which are quite about the opposite. They don't care anything about the social part. But anyway, it's huge and it's beautiful, but the last part of the title now is empire. So what does it mean doing that empire? And basically it's maths. Yes, we want to do some computations, and I think Python is a wonderful language to do these kind of things because it's fully in the realm of exploratory programming. You don't have rigid procedures depending on what you want to do, you have to develop custom software. And Python has got some very excellent, wonderful, whatever libraries to do that kind of things. So this is the classical stack, okay? SciPy, NumPy, IPython, and Matplotlib. This is widely used because when you have to do have a number crunching in Python, that is what comes to mind immediately. Then there is more specific stuff like network gigs, which is a big library just for good network analysis. Most of the algorithms we'll see are implemented in network gigs, so you just have to call a couple of functions. Basically, if you know what they're doing, which is what I try to explain, then you can just do social network analysis without writing loads of new code. GAS is a visualization tool that is made in China. I think it's nice because they took Python and they made a domain-specific language called Python, which is just able to manipulate graphs so that they can do visual stuff with that. We won't see that because it's quite complex in its own right. Okay, but then this is another tool. This is more on application side. You don't do programming with that. You just visualize networks, explore the networks, and it's fully Java stuff that is on the NetBeans platform. Still, they can be scripted in Python. So I believe that many Python programmers really are, well, many social network analysts are really doing things in Python because Python is everywhere here in social network analysis. This is about the size of social networks and how they're done. For example, we have networks about 200 people, and networks of about, well, quite bigger. We see that the edges, the number of edges, does not really scale with the square of the number of nodes, which is what would be in a complete or nearly complete network. That is the total maximum number of edges that is possible on a network of this size. Okay, this is not correct because these are all approximated, but this is the square of the real number which was approximated here. Okay? And so I reported the density, which is the fraction between the number of edges that are in the network and those that are in the complete network. So you can see the density is fairly low. In these cases, well, just one node in almost, well, 100 nodes in a billion. That means that they are sparse, and we don't have to represent social networks as compact structures. This is the number. It is something which gives the theoretical possible social network of primates. So gorillas, people, okay. And there is an estimate, of course, about every one of us knows about 150 people. Well, knows isn't rather straight contact with, and so we can estimate the size of the world social network. And this is okay, but it's that. So I already started to talk about data representation. This is the mass representation, which I would like to skip almost. So we have a triangle, we have a set of edges, we have a set of nodes. We have a function which maps each edge with its endpoints. So basically we can, this is the definition of graph. The order of the graph is the number of nodes and the size is the number of edges. So we can see that the size of graph of a social network is about proportional to the order of the graph. And we will be dealing with simple graph. So without self-links and multiple links. Okay? So we don't have people friends just of themselves, for example. About computer representation, we have adjacency matrices, incidence matrices, which is not interesting for us now. Adjacency lists, incidence lists. So this is basically a matrix when you put one, if two people are connected, okay, you have people on the rows and on the columns, two people are connected, there is one, otherwise there is zero. So this is what we mean with using sparse matrices. They are very sparse, and we should not use, for example, NumPy, but SciPy matrices. Okay? This is have dict, and keys are nodes, values are lists or sets or something like that of nodes. On the other hand, here we have two structures. One maps keys, this is edges, sorry. So one maps edges to their endpoints, and the other dict maps nodes with sequences of edges. Okay? About sparse matrices, of course, we have to use SciPy. Perhaps SciPy offers a bunch of different representation for sparse matrices. We have just to understand what kind of analysis you want to do and choose the more appropriate representation, because not every operation in that structures is efficient the same way. And sometimes conversion are possible, and while you have very, very large networks, this is probably not likely. But anyway, many algorithms are very, very easy to write if you have a matrix great notation, because it's the way the maths behind that has been developed. Though it's cumbersome to put that data on nodes, so if you want to do something different from just create social network analysis, for example, you have a graph of tweets from Twitter, then you may really need this kind of stuff. Okay? And this representation is probably not very good. Instance lists is very used in Yum, which is Java library, which is probably what you'd be using if you work with Java. But anyway, you can also choose to implement this kind of stuff on your own, because you know that it's the right thing to do for your application. So we have edge objects. We have seen that because we want to put them as keys in a dictionary. And we have, they contain their attributes. Okay? So if node have, for example, weight or keyword attached, you just put it in the edge object. Same thing for nodes. So somewhat it's very object oriented. I believe that most of the time it's an overkill, because really you don't want to do this kind of rich objects. Then which one do you want to use them? Okay, you perhaps have a database, and so you need some kind of object relational mapping or NoSQL, which you have to convert to objects and vice versa. So perhaps it's quite inefficient. Moreover, just following the textbook definitions is inefficient. I'll show you why. For example, we have this dictionary. Well, we put the lists, for example, this kind of sets of nodes. So in the instance, we map every node with a set of edges it has. Okay, and each edge here is connected with its endpoints. This is an example about how it happens when we add a node. We just put it in this dictionary with, of course, default value. When we add an edge, we put the start and end points. Okay? Then if the node's start and end points do not exist, we throw an exception. Of course, we should throw back this. Perhaps it would be better if we placed it here. Anyway, it's just an example code. Then we just add link to both dictionaries here, both sets. Sorry. Okay. The problem is to see if there is a connection between I and J, for example, we would have to do a linear search. So a data structure like that has heavy inefficiencies, which we can fix like this. Here we use a dict, so nodes are mapped not to set of edges anymore, but are mapped to a dict where the key is the other endpoint and the value is a node. So this way we can just check if we have a link with two dictionary lookups. About adjacency lists, this is somewhat the more Pythonic representation. There is also this beautiful essay from Guido Barroso himself. Okay, he argues that this is the best representation in Python for simple graphs. You can just do it with dictionary lists. Okay, that's nice. It's efficient in terms of space, costs of elementary operations, and it's also what we are using under the more famous networking library in Python is NetMix. This is an example code. Of course, it's almost toy, but anyway, the idea is that we have a dictionary where we put the nodes. And when we have a node, if it's not in the dictionary here, we add the attributes to the node, because now nodes are basically labeled, not objects. And so if you want to store attributes, we have to put them in the graph, or perhaps to write down the code to get those values from the DB. Okay? When we add an edge, we just added to both, this is a dictionary of dictionaries, so U is the first node, Vu is the second node, Vu and U, we eventually put here the attributes of the edge. This is basically what does network X. It's almost always efficient, but for example, handling edges is not, because we have to do a linear stuff here. Just iterate on the dictionaries. Well, I introduced this stuff, even if most of you have seen it in computer science courses, because we have to remind that depending on the algorithms we want to use on the network, some representation may be not efficient. Moreover, if we want to deal with very large graphs, probably we could use network X or similar libraries, and we want to manually choose a representation for the network in the DB, which can be a NoSQL DB, of course. And the representation, well, it has a strong influence on what we can do with network, and probably we have to do it custom. Okay? Of course, network X is able to convert between different representation, that is, matrices from pi, sci-pi, or other sparse stuff here, for example, digs of fleece, this kind of stuff. Okay? So it's very useful even to convert things from different sources. These are file formats, so you don't have the graph in memory, you have it on disk, and perhaps it's not a very large graph, because most of this stuff is XML based, so a very large graph in XML is good just to finish your hard disk. Anyway, so network X can be used even just to convert between these formats, which can be useful because different tools perform different analysis. So it's quite common, for example, to look at the graph in application and then do the analysis in another application, perhaps write a couple of custom C++ routines to perform a specific analysis, and so you have to convert the network easily. And now we jump to network properties. Here it's a very boring way to define the degree, which basically is just the number of edges incoming in a node, okay? The in degree is the number of edges incoming, out degree, number of edges going out from the node. But since we have mostly undirected networks, it's just the number of edges of the node. These are the network level properties we'll see in more detail. This characteristic about length, clustering coefficient, degree distribution, okay? And of course, every network level property, for example, big rank for a node, can be studied as a distribution or in the correlation of the distribution. So that becomes a network level property. Okay? What is the characteristic path length? We have the path length, which is the shortest, the shortest path length is the shortest path which connects two nodes, okay? And we can just do the average of all the shortest path lengths from a node to every other node. Of course, it works if the network is connected. If it's not connected, like it's quite common in social networks, we just take the core. So the central part of the network, which is connected by definition, and contains a very large part of the nodes. So we just study that thing, and that cuts out problems that are related to not being connected. Okay. Anyway, then we do the mean of the path length, of the average shortest path length. So we get a number which gives us a measure of how far are nodes each one from another. Okay? About the computational properties, we can use Darcy algorithm, which in practice on each node. So in practice, this is the running time. If we use Fibonacci hips instead of more easy to implement structures, we'll see a very simple implementation in Python here. But if you want just to do it fast, just use Fibonacci hips. Well, you don't need to do that because I'll show you a way to cut computing times just using approximated data. So with network gigs, we can compute all this stuff, but you see the algorithms nonetheless. This is Darcy algorithm. This is heavily based on this recipe from active state site that was written by Einstein. Okay. Basically, we are using the heap queue module as a priority queue with tuples. The first element is distance of the node under analysis from the starting node. So this gives the shortest path from one node, and we have to repeat that for every node. That is because here we have just n log n, for example, and in the previous slide there was square n log n, because I assume that you are doing that for every node. Okay. These operations here are basically these and these, which account for most of the running time of the algorithm. Priority queue puts nodes into queue just once, and you get nodes back, so this outer loop runs n times. And since this analyzes all the edges, or all the neighbors, but that means all the edges for each node, altogether that is n operations, because you do it n times for the number of edges of each node. So we basically take a node from the queue, starting from the source, see its neighbors, and consider that if you want to see how far is that neighbor from the starting node, well, that is distant one more than the neighbor than boom, okay? And so we have to check if that is the shortest path. That is to say, if we haven't already found a shorter path. If this is not the case, we just write down that that node V is the shortest way to get to W. Okay? That is basically last algorithm. And it can be done in a few lines of Python. But this is not extremely different from the way it's implemented in network X. So it's not really a joint implementation. It just does less checks. For example, assumes that we have no weighted graphs and that no labels, which tells us that the edge is longer than 1. But anyway, these are details, just details. The problem is that this algorithm is not efficient, and the mean is also expensive to compute, because they have a lot of nodes. So perhaps just doing the trivial thing is not feasible for large networks. We prefer just to compute the median, because that is more efficient. Then, we also know that the median can be estimated in a very efficient way, which makes it even more efficient, and I'll show you what I mean. We'll give a couple of definitions here. We define an MQ median, if at least Qn of the numbers in a set are less than or equal to MQ, and at least 1 minus Q are greater than MQ. For example, the regular median is a 1/2 median. This way we could, for example, choose a value which is like 1/3 median. So for example, if we have values from here to here, we just want the one which is about here, okay? And then we define a next approximation, that is Q delta, okay? A Q delta median, if at least Qn 1 minus delta are less than or equal to, and similarly, these are greater than. So, delta basically said, okay, it doesn't matter if it's just the median. I just care it's close enough. If the data distribution is well behaved, then it doesn't matter. Okay? And this is extremely fast. This is Huber algorithm. He gives us a precise size of a sample we have to choose in order to have a good estimate of the median. So he says that a value for LQ delta of B distribution can be found taking a sample of S elements and looking at the MQ median of the sample. And then we know how big has to be the sample. Okay? And this is size. If it's at least that big, then the value is correct with probability 1 minus S. Here. So we can choose how precise we want to be. And this is great, because really most of the times we don't care about the shortest path length, or implicit path length being exactly 3. If it's 3.1 or 2.9, it doesn't really matter. But we can do this very efficiently. This is the code. This is not implemented in network X as far as I know, at least if it is, I didn't find. We just estimate number of elements we have to take in the sample, so it's S. And this basically does the maths in the last slide. Then we get the sample. Of course, if the network is smaller than the suggested sample, we take the whole network. And we just compute the shortest path lengths from the nodes in the sample, for the nodes in the sample. And then, of course, do the averages and take the median value, Q median value. That is here, epsilon is here. Those are typical values, okay? And you can just, perhaps that is in the size, in the order of 1,000 nodes. Even for larger networks, And besides, if the network becomes larger, you can just decrease delta. Okay? If the network is larger and you decrease delta, increase delta, well, decrease the precision, then the error is less severe. Okay? What I mean with we really don't care, this is a graph. Okay? Here we have number of hops. Well, if it was integer, but anyway, that is the characteristic of length of the network of increasing size. So that is 2,000 nodes. This is 10,000 nodes. And here we have the running time of the algorithms. The mean, just regular Baxter algorithm that perform on all the nodes, is here in dark blue. The estimated characteristic of length is in light blue. So we see that, well, they are pretty close. You're not really going to care if you got this point instead of this one. Okay? So it's very, very, very efficient. Because this is in green is the time of the regular algorithm. Please see the pattern here. So it's not only slower, it's just a different function time of the size of the network. And here in black, we have the computing time of our approximated algorithm. So perhaps we see that we could just go very far with modest increases in running time. On the other hand, here we are basically at collapse because this is 5 minutes on 10,000 nodes network, which is a small network. Okay? Considering that, this is not feasible, not at all. Google works with matrices of millions of people. Okay? Perhaps doing this kind of stuff, you are going to get values, but this is not going to work. And now we have to see another metric, which is the local clustering coefficient, which leads to clustering coefficient. So, what's the thing? The characteristic pattern tells you how close are nodes in the network. Okay? Local clustering coefficient tells you how tightly knot is the network. Okay? In social networks, friends of friends are usually friends with a high probability. In technological networks, this is not always the case. If you got two routers, perhaps you don't connect the two routers in the tree. But people don't do it like that. They're not routers. So you have a friend, you have another friend, perhaps they are friends because they know each other. Perhaps if they like you, there is a reason they love to different themselves. So we know that social networks have a high local clustering coefficient. Nodes of social networks have a high clustering coefficient, and social networks have a high clustering coefficient. This is a graphical representation of how known we have these networks here, which are connected with green light. And in red, we have the connections between the neighbors. So these two are friends themselves, other than being friends of this central node. And dashed lines here are the lines that could be if this was a complete network, but are not in our network. So that is light density, or attraction between the nodes, the edges which are actually in the network, and the edges which are not in the network. That could be if it was a complete network. And in this example, the local clustering coefficient of this node is 0.46 because it got 7 connections between the neighbors and 15 possible networks, possible edges. Okay? Local clustering coefficient. Okay, this is the mass of the example of the previous slide. This is the number if you just want to computed. And then the clustering coefficient is just the average of those values. A different definition is here, which is a different definition in the sense that for the same network you get different numbers. Some argue that this definition is better because it's somewhat more robust. Here you count the number of triangles. Okay, you see the network. A triangle is a set of 3 nodes where each node is connected with each other node in the set. Okay? Connected triangles are just a set of 3 nodes where you have at least 2 edges. Of course, a triangle has for 3 connected triangles because if this is a triangle, you have these 2, you have these 2, and you have these 2. So it counts for 3 connected triangles, and you do the fraction. However, although this is probably better, this is easier to compute because you do something at node level, so you can perhaps just sample things. Otherwise, here you have just to count everything, and it's not going to work. However, network is does this for you, and next clustering I usually import network X as an X. So you see that graphics. That's it. An X cluster. This is an X average clustering. And this is an S sensitivity. So you can just play with that and see how different networks compare those related to those 2 networks. And basically, we are done with the clustering coefficient. And we can see the degree distribution, which is another network level property. And it's a very hard one. I'll explain that in a while. So, the degree distribution is just the frequency of degrees of nodes. Okay? What we know is that most social networks have right-skewed degree distribution. That is to say, you have usually, if you think about a normal distribution, you have a big center, big some wings. Okay, these are right-skewed, so you have no center peak, you have a right peak. Okay, that means that most nodes have low degree, and some have exceptionally high degree. Okay, so there is very popular peak. And this has to be kept in mind when you're doing a sample, for example. Because if you sample all the nodes, that is to say, you take n nodes with like random sample, something like that, you are probably oversample networks, nodes with low degree. When you do edge-based sampling, which means you sample some edges, and then you choose one endpoint of the edge, you're probably oversampling high-degree nodes. So you have to decide what really you want to do. Some researchers says that these are usually power lows. A power low is things like this. So K is the degree here, is K exponent minus alpha. That is the exponent of the power low. They are also called scale-free networks because of that, because you can just take the fraction between the frequency of 2 nodes, and then, for example, you multiply the degrees for constant factors, the fraction remains the same. This comes from just the definition above. The problem is that most networks have, well, if they really are power lows, and I show you why it shouldn't be assumed, they have exponent of 1, 1.6, 2, 2.6, 3, something like that most of the times. And this is a problem because these are the moments of distribution. So here we have the distribution that gives the exponent n, and it is the nth moment. So for example, the mean is the first moment of the distribution. on the expected value, I mean. And the variance is related to the second moment. You need the second moment to compute the variance. What's the problem? Well, the problem is that if this number is below 3, which happens quite often, this thing is not summable, has not a finite value. So you don't have the second moment of the distribution. And what's the problem? The problem is that the central limit theorem is a basic thing in statistics and probability theory, requires that you have finite mean and variance. So if you have a power law, the central limit theorem does not work. Central limit theorem is the thing that says that you will take samples from a distribution, samples are independent from the same distribution and all, and you have that variance and expected value and variance finite. Then, basically, the average of the sum of the values you sample is a normal distribution. So if you have a very bad distribution, you can't study somewhat sums and that kind of aggregate things and have something you can work with. With this, it doesn't. And this is the phase that thing has. This is just a linear plot. And this is what we mean when we say that most of the nodes here have a very low degree. And some of the nodes have a very, very high degree. What is the problem? The problem is that, theoretically, these are important. So if you have got a normal distribution, outliers are very rare. Perhaps you can assume you have no outliers. When you have these things, you do have outliers. You always have outliers. And if you don't consider these, for example, you are dealing with a completely different network. So you just can't ignore them. They are important. If you do a log plot, the thing has this space, okay? The model which I used to generate this network is a synthetic one. I know the model, and I knew that the exponent of the redistribution of networks generated with that model is 3. And I manually adjusted the multiplicative coefficient to fit the data. And so what is the problem? There is no problem, because I knew from maths that that is correct. The point is that many people just have the data, and they say, okay, it's roughly like that. I draw a line, and yes, it's on a line, more or less. So that is power law. Well, that is not the case. That is not true. But anyway, more recent studies show that many things that were dubbed power laws are not power laws, and that better distributions fit. However, there is quite too much maths behind that to show it here, because I should have done basically a presentation about methods to choose degree distributions, fitting functions for right-skewed distributions. However, if you really are interested in this kind of stuff because you have some data and you want a degree distribution, please check it out, because there are already made algorithms which not only tells you the degree of confidence if that is a power law, but also suggests a better fitting distribution. Okay, for example, something along normal distribution or power law with cutoff. So you have a power law and also an exponential term which makes things a bit more regular and cuts down outliers which are too big. Okay? Basically, whatever we know, all we know is that they have a heavy tail, okay? And they are usually assorted. So, very high degree nodes tend to connect with very high degree nodes. Why this is good? Well, depends. If you're starting diseases, then it's not good, because associative networks are very, very easily attacked by epidemics. Okay? On the other hand, if you want to spread information, that is very good, because information travels faster. Not all social networks are really power-low networks. In fact, this is an older model which was not developed to explain social networks. It was just a mathematical toy by those two guys, Ebersh and Brady. Okay? And this is the model. You have a probability distribution of all networks with n nodes and n edges. Okay? And a model which is equivalent is this. You have n nodes, and you random draw a number for each node, for each edge that is in the complete network, and with probability B, that edge is also in our network. So why this is important? Well, it really isn't, but it used as comparison. So this has a short characteristic of length, which is logarithmic in the number of edges, of nodes, sorry, but has a very low clustering coefficient. So when we say that the social network has a high clustering coefficient, we mean that it has clustering coefficient orders of magnitude larger of those of a random graph. And this is the phase random graphs have. Okay? And these are some properties of a random graph, which can be just computed by analytic computation. But anyway, this is not completely not relevant. For example, it's something that I find quite funny. They started a high school romance network. So people, they said they looked at who dated who, and they find out that that network was more akin to a random network than to a social network. So perhaps some human processes are very different from others. So friendship, knowledge, falls heavy tails, and something like power-low degree distribution, and that is. But romance is more random, okay? And that is what I told you before. So if you want to pursue a generative approach to social network analysis, that is to say, we want to find which models yield the networks, okay? Networks with comparable metrics from the one we're studying. And the right thing to do is develop models. And there are a few interesting ones, but I want to show them here because, well, that's a completely different topic, and it doesn't matter if you're doing that in Python or not. These are numbers from real networks, just to give you an idea of the numbers we're talking about. So clustering coefficient, this is considered high, because you know that it's from 0 to 1 because of the definition. But what means high? This is high. Okay, if it's 0.1, 0.15, then that's high. Random networks have 0.000 something. Okay? The characteristics of length are like these. If you consider that perhaps all the people in the world is connected by a chain of, an average of 6 steps, then this is not unlikely. I mean, these are social networks, and somewhat what the web jumps physical distances. I mean. group level properties. They are very important because knowing the subgroups means that you can study a smaller subset of the network. People from social sciences are very interested in that kind of stuff because finding groups of similar people is basically the job, because they just can study this kind of similarities. Okay. In the last century, they gave, well, I just don't care to number, to even count them, definitions. These are examples. And Cliche and Clown and Club and K-class, K-core, LSN, which are definition of what is a group based on structural properties. So they give that. Each one of these definitions has good things and bad things about it. Most of them are extremely expensive to build, so we just can't use them for large networks, because we basically want to see if a subset of a network has given properties. Each subset of the network basically could have those properties. So if you have a large network, you are basically working with a subset of the networks, which is huge. Something they also did was try to define similarity as the role in the network, and this is a different branch of group level properties. Well, if you're interested in that kind of stuff, network has a bunch of algorithms to do that kind of stuff, and the docs are pretty clear, so you can do it. All we know and what we care about is that social networks have a highly connected core where everybody is connected with everybody else. Then there is a fringe of people which somewhat are like whiskers that download from the core, but still are connected from the core. And there are also stars and isolated nodes, which are people, for example, who just signed up but never used the network, or perhaps just connected with the person who invited them to the social network. In this case, think about Facebook. And this gives an idea about visualizing social networks. I generated this network with an algorithm which says at every step a new node is introduced. At each step a node is chosen. He connects two of his friends. He introduces two of his friends. He does not have any friend. He just connects to a random friend, to a random node. Okay, and there is some probability that a node leaves the network at each step. Okay, so this is an example about simple processes which tries to explain social network formation. This is a graph generated, so you can see, for example, these things which look like stars, that is to say small groups of very connected people, but not really connected with the core. We have a highly knocked core there, and we have whiskers. These people are more connected among themselves than with the core, and still are attached to the core. You can do simulations in Python of this stuff, and you see that all those things eventually will connect to the core more frequently than they connect among themselves. But anyway, we jump back to programming now with centrality matrix. Once again, there are a lot of them, some related to degree, some related to shortest path, some related to different stuff, for example, ranking metrics like PageRank. Okay, we can study the distribution, the correlation of that stuff. Here is one of my favorites, that is the betweenness centrality. And what does it mean in short? Kj is number of shortest path between K and J that lies on E. And without the E, there is just the number of shortest path between j and k. So if I lies on most shortest path between j and k, then I is very important to connect j and k. And then this thing here is basically the betweenness centrality of a given node. I don't show you the code because it's already implemented in network X. Though I'll show you another thing here, that is the tag. Suppose you want to break a network, okay? And you want to remove just a small number of nodes. What do you mean with breaking the network? For example, in this context, it is just making not connected anymore. So, for example, you have an encounter with your boss, and you want to destroy your company network. And you want just to turn off some routers, not every router, okay? And you have to choose which routers you have to turn off. And the more they are, the more likely you are to get caught, for example. Or maybe you want to just shut down the power plant, the power grid of the city. And once again, you want just to turn down a very low number of nodes. Or perhaps you work with the city and you want to design a power grid which is resilient to this kind of stuff. Because there is always some social network analysts which went crazy and decided to destroy something. So, here we just choose the ranking function, centrality matrix, and order the nodes according to that metric, and remove the nodes according to that metric. Okay? So what happens? These are some examples. When you see a social network, that means that it's a synthetic social network created with a given algorithm, which is power law, centrality, network, something like that in network X. A random graph is just a random graph. And then I tell you which is the ranking function I used. Random attack is no ranking function. I just choose a random node. Okay? And betweenness, of course, is the betweenness centrality. So we are exactly targeting the nodes which lie on most shortest path. So it should be pretty effective just to break those bridges. Okay? PageRank is Google PageRank. And degree is just we choose nodes according to their degree. So we see that with random attack, I run this many times and I chose this because it's very interesting. For example, on random attack on a network of 1,000 nodes, we have to remove 200 nodes, more than 200 nodes, just choosing random nodes. Okay. This has about an average degree of about 7. If you have a very high average degree, then expect to have to remove a lot of nodes. On the other hand, just choosing 10 random nodes, we broke the random network. We have been lucky. We just took the right ones. On the other hand, here, when we choose nodes with a good metric, doesn't matter betweenness, PageRank, removing 20 nodes, 20 steps means I removed 20 nodes, I broke a network, a completely connected network of 1,000 elements. On the other hand, the random networks needs one order of magnitude more nodes to be removed. So in fact, social networks, highly structured networks have many advantages. For example, information spread, some kind of resilience towards random attacks, random failures. Because most of the times you are just breaking a node if it's random, which is not important. On the other hand, if there is malice, then they are very fragile. Because if you know which nodes to break, then you're going to break the whole thing easily. And now we jump to a very light topic, which is visualization. Network X has many functions for visualizing networks, which basically rely on graph bits, basically. But we can also use GAFI or GAS, or this is probably more interesting right now. This is done at Stanford. And it's basically JavaScript stuff, so you can put it on the web quite easily. We can choose the algorithms to place the nodes. For example, we can choose a regular structure, or we can minimize some force function which tries to put nodes which should be close together and place other nodes more distant. We can color nodes, whatever. So this is a network I decided to draw. Okay, here the size of a node depends on an array, depends on the size of the node, for example, and the column on the between centrality. So a network like this, you just can't see the links because they are too many. You're not going to understand a thing. But perhaps with this kind of visualization, you see the core. You just see that these nodes have higher degree, have higher betweenness, and they are the core. Okay? So if you just see this network, you have a rough idea of what kind of networks we're talking about. Now we jump to properties, which is JavaScript. So we have to convert our networks in a JSON object. And we are doing that here, basically. Before we convert our rounded network there to a dict of lists, because perhaps if we don't have network dicts, we already have a list of dicts, a dict of lists. For example, we got it from our DB, something like that. So the code below does not depend on network X anymore. We do a dictionary. Well, we have node name, a group, and we have edges, both from the target to the source, and vice versa. Okay, because this works with directed networks. Okay, and we just write the JSON object to a file, and then we can do this kind of thing. This is the matrix. This is the I think it comes from a book, the social network. I don't remember which one. The Mesoros, I think. Okay. They did some grouping in order to put close together nodes which are related, and this is basically an adjacency matrix. Okay. So you have dot where you have connection. I think it's presence in the same scene in this case. And this is a way to visualize a network. And this is the JavaScript code which visualizes that thing. You can put it on a web page, and you have that in your browser. Here, in the where is it? Network nodes and network links. That is a JavaScript variable where we put the network. Okay, and here we do compute the layout, the way to put things down. Okay, then this code makes that render. Okay, so it's very easy if you have a web application to use that. This is more traditional, somewhat. Where is it? Okay. I forgot the animation. Anyway, you can see that in that thing here. This is the very same library here, which I choose a different visualization. And we can do that kind of stuff. I just removed that thing so you can see the network. Okay. So that is the network, for example. The very same one you saw in square matrix 4, depending on what you want to do, one representation is more important. So probably this is the main characters of the book. These, perhaps, those. Okay? And this is the code I already showed you. And unfortunately, there is no time for page rank. Thanks.
Are there any questions? Yeah.
What's the best interchange format that you found? So, like, if you work with Wi-Fi, if you figure out as soon that it doesn't take byte files or HTML, it takes them, but each of the formats have some strengths.
Yes.
So and even the JSON example that you showed wouldn't have all the metadata example if you're trying to grab more complex stuff. What do you recommend to use?
Well, first, I would say that having everything XML based is something which really troubles me because it's too big. How the things are just metadata. But anyway, I try not to use Gephi and that kind of stuff just because I didn't want to learn another tool. Right now, I believe that for basic networks, NetworkX has very good visualization tools. So I try just to use that one, which is basically I just do import NetworkX and X, and I work from that there. So I just get all the metrics I need printed, and also the visualization is not bad. Perhaps Gephi is better, that is one of the tools I mentioned. But still, for simple things, I just prefer NetworkX. Besides, if I got some DB behind me, I just can think about putting that in an XML file and load it into Gephi. It's not going to work. I usually use GraphML because I find that most tools you can't understand that. But anyway, really, there is not a very compelling argument in favor of one or another format, in my opinion.
Other questions? What do you think about the development of graph databases? So, typically in social network analysis, we have to deal with batch analysis, but maybe graph database can help also in this task.
I think so. We are starting to experiment with Neo4j, which is a Java-based graph database, which is not very easy to talk with Python. You have to use a specific library to do that. It's not very easy, but it's very promising. I was interested into Allegro as well, but there are some licensing problems in that you can't give it to a student to work with that because it's a homework, but you can't use that yourself. At least that is what I figured out, and I didn't want to risk. So I very like graph databases because I think that if you have to run very large analysis, that is the way to go. Perhaps you put just the algorithm in some kind of, the language that the NoSQL graph DB supports. So for example, for Redis could be Python or JavaScript. There is not graph DB, but the idea is the very same. You have the DB and just put the analysis in code that is run directly in the DB. I think that graph databases are very important because they do some easy stuff. Though, I believe that most NoSQL databases allow for very easy graph representation. So, I'm not sure that a graph DB is the only possible choice if, for example, you have a more expressive language in another database.
With vector X, is possible with vector X calculate the percolation coefficient?
Wow. It's more yes than no, in the sense that network X has a very extensive set of functionality, and I wouldn't be surprised, I would be more surprised if I found out that there was no such functionality than the other way around. Though I never use it, and so I never check it out. Still, if it doesn't, you probably know how to easily implement that in MATLAB or MATLAB-like languages. So you can just move your graph to SciPy, and that is something Network X does very easily, and then run taking on the matrix representation of the graph. So that's perhaps not, even if it's not iterative, that's about, well, half an hour work. Okay?
Another question for you, Enrico. Yeah. Okay. Yeah. Thank you very much.